Now with trig functions, you've probably seen these defined using the right triangles, the sine of alpha. For some reason, Greek letters seem to be used for angles, but not sure why. But alpha, sine of alpha is defined as the opposite over hypotenuse, cosine adjacent over hypotenuse, and then tangent opposite over adjacent. Now, there's a little mnemonic that's used. Some students, it's really helpful, and it's called SOHCAHTOA. Anybody heard that? Okay, probably sounds like most of you. SOHCAHTOA. The sine is opposite over hypotenuse. Cosine adjacent over hypotenuse, and then TOA would be tangent is opposite over adjacent. Okay. Now, in trig and in calculus, we use three other functions as well, and they can be defined in terms of the right triangle. The first one we'll define is the secant. Now I'll write the notation. Of course, with this graphic, they don't write the shortcut notation. Sine is sin, cosine cos, tangent tan. Secant is SEC. Secant is defined as the hypotenuse over the adjacent. Now, there's other ways. I don't think about it in this way, but I'll show you kind of the little shortcut here in a little bit. But that's your secant. Cosecant, which is your CSC. This would be defined as the hypotenuse over the opposite, and then the cotangent. Cotangent of alpha is defined as the adjacent over the opposite. So all of these trig functions are defined in terms of a ratio of the lengths of the sides of a right triangle. Okay. Now, these last three, for me, it's a whole lot easier to keep it in terms of sine and cosine and tangent. And by definition, these can be immediately turned into the reciprocal of one of those first three. Secant would be the reciprocal of, well, the cosine. Okay. Cosecant is the reciprocal over the sine function, and then cotangent would be the reciprocal over the tangent. Now, the nice thing to remember here, to remember secant would actually go with the cosine, and the cosecant goes with the sine. What we have to think about, each pair has one co-function. Okay? So to remember when you're getting these thrown at you individually, the cosecant, well, cosecant already has co in it, so that pairs with 1 over the sine of the angle. Secant doesn't have the co, so that has to be 1 over cosine. And then, of course, you got to remember tangent and cotangent. Those are a little easier to remember. But that's how I remember, especially the secant and cosecant, which one goes with the sine and the cosine. Okay? Questions? Now, this is one set of definitions for trig functions, and this was more what the videos you were to watch kind of focused on. But I'm going to take this a little bit farther and show you something you may not have seen yet. The unit circle, we talk about a circle of radius 1, and you can see here graphically we put the center of the circle at the origin and then radius 1. Any point on that circle can be represented in terms of trig functions based on this angle right here. And in this graphic we use theta rather than alpha for our angle. And once again we see the right triangle being used. The x represents our horizontal and the y the vertical, but because of that we have our right triangle, and all of the right triangle definitions would fit in this as well. And what we're going to look at, each piece of this triangle, even on the coordinate system, the x, this side of that triangle would actually represent, whoops, not the sine, would represent the cosine of theta. Just as the x coordinate is represented here. And then the y, the vertical part of that triangle, is the sine of theta. Now, that's fairly common in trig class. When we start defining trig functions, sines and cosines are very much, very commonly defined as in a unit circle. But what does a tangent represent? What does the secant, cosecant, cotangent? We're going to look at that here as well. And slide shows, well, a little smaller detail of the unit circle. But this piece right here is the unit circle in the first quadrant. But now we can see not only the x value would be our cosine theta, y value on the unit circle would be the sine theta. The tangent is a vertical line tangent to the circle at the point 1, 0, and the line is extended past the unit circle to intersect with that vertical line. And that much is what we would call the value of the tangent theta. So we can kind of look at this as two separate triangles, right triangles, this being on the unit circle. The x value would be cosine theta, the y value would be sine theta, and the hypotenuse would be 1. Okay. And that also kind of illustrates one of the most common identities in trig, Pythagorean theorem, Pythagorean identity, sometimes this is called. Cosine squared theta plus sine squared theta will equal 1. Okay, it comes directly from the right triangle. Now, let's extend this out, out to this vertical line, and our right triangle, well, it's a little bigger. This part we're going to call the tangent theta. What would the base of that triangle be? Okay, that's part of the unit circle. It's tangent to the unit circle, so that's going to be 1. And we find the secant of theta actually turns out to be the hypotenuse. So from there, the relationship between tangent and secant shows up in a right triangle with 1 as the base of that right triangle. And, of course, that introduces another Pythagorean identity. A lot of times we show it algebraically from this one, but geometrically we can show it 1 squared plus tangent squared of theta. Of course, 1 squared is just 1. That's going to equal secant squared of theta. Okay? Questions there? Well, this shows our relationship between cosine and sine, tangent and secant. What about cotangent and cosecant? Let's see what we have there. Now, this graphic shows all of what we've done so far, plus adds in the cotangent and the cosecant. Now, again, down here would be the origin, dealing with angle theta, and there's our cosine and sine. What we just looked at with the tangent and secant. Well, the cotangent is actually go to the top of the unit circle and draw a horizontal line and intersect that with the ray coming from the origin, representing our angle theta. And this distance here represents cotangent of theta. So we've got, for this angle of theta, we've got an even bigger triangle to deal with. I'll just rewrite it all by itself here. You can see how well I draw. My straight lines aren't real straight, but that's actually not too bad. Now, that is coming from an angle of theta down here, but we have this side would be 1. Again, that horizontal line is tangent to the top of the unit circle. And this would be our cotangent of theta. And then the hypotenuse of this one is where we see the cosecant of theta. Okay. And our right angle actually happens up here. Now, with all of these relationships and everything, the definitions and so forth, and all of the geometric properties we could use, we can draw lots of other pictures and show what part represents tangent, what part represents cotangent, and so on. I saw some graphics where they drew a perpendicular line here, perpendicular to this line, and define tangent theta and cotangent theta from that line. We're not going to worry about that. I mean, we could spend, well, probably a week going over all the different ways we could represent that, but we're not going to do that. But I just wanted to show you geometrically or from the unit circle where some of these values come from, how they are represented geometrically. Okay. So, any questions about that? Now, so far the graphics, they've pretty much kept theta about at the same place. We could adjust and put theta, make theta fairly big. Well, same ideas, it would change the value. If theta gets bigger, well, the tangent of theta, we're not even going to have room to show that, but it would continue on up through the top of the screen. Tangent theta would be fairly large, but then we'd see cotangent of theta would actually just be this right here. So as one gets bigger, the other gets smaller, and again, that's your reciprocal, cotangent being 1 over tangent. But geometrically, we could draw lots and lots of different pictures, lots of different triangles, right triangles, representing different values of that angle theta. Now, this next graphic actually takes us beyond what we've worked with in a regular trig class. And some of the notation is slightly different with, well, cotangent. Yeah, cotangent they show as CTG instead of COT. Not real sure where that came from, but we see our cosine and sine. We see the tangent and the secant as we define them. And then, in this case, they show the cotangent here, but our cosecant, we're going from here up to here. Now, once again, that's a manipulation of the definitions where cotangent would be, for this particular problem, we could rotate. Cotangent could also be defined from here to here, from whatever letter that was that C that I just covered up? From C to E could also be represented as cotangent, and then that would give us our triangle, right triangle we dealt with earlier, 1 as the base, and then cotangent as this side, and then cosecant as the hypotenuse. Okay. Now, that shows our 6 that we're used to, and then this one actually shows us several others that you've probably never heard of before. Now, I really had never heard of these either. Several years ago, I had a friend who was a land surveyor, and he asked me, well, you're a math teacher, have you ever heard of these trig functions? I'm like, no. And that was probably about 20 years ago, and I still had never dealt with them until I started looking these up on the internet for this little presentation. The versine, as we see here, versine is, well, that's just the 1 minus the cosine of theta. That would be from A to B here. Versine. So it relates to the cosine, to calculate it, we'd just calculate the cosine and then take 1 minus that. But that's geometrically represented as the difference here on the x-axis. Again, we're used to seeing cosine theta being the base of that triangle. Just extend that out to the end of your unit circle. Versine would be that. Now, versine is actually used in certain areas. Again, I had never heard of it, so I had never dealt with those areas before. But versine is actually from the term versed sine, or in Latin it's known as sinus versus. I'm not much into Latin, but that's where most of our words come from. Sinus versus means flipped sine. Okay. And again, the most notable application of this in surveying, land surveying, or in navigation, ships navigating the sea. This deals with, well, actually, not the versine, but another term that deals with the versine, haversine, which is half of the versine. Yeah, we start to get our minds blown a little bit. But the haversine is used in navigation, the land surveying. It deals with 2 points on a sphere. And, of course, the Earth is a sphere, a very, very, very large sphere, but that's why with maps we have a hard time drawing straight lines from maps and translating that onto the globe, onto Earth. In our road system, okay, you go so far straight north, well, you're going to have a little correction line. You'll have to turn and go east for a little bit before you head back north, or that's a correction line trying to translate our two-dimensional map onto our three-dimensional world. But versine or haversine shows up in dealing with surveying and navigating ships and so forth. And then, of course, there's others that are defined here as well. I'm not sure where or if they are used in any applications, but they are defined. The coversine, coversine is right here. That's going to be, well, that would be the 1 minus sine theta. That's taken our vertical unit radius and splitting it up. This much would be the sine of theta, so 1 minus sine theta would be the coversine. We do see what's called the x secant, and that is, okay, secant is the hypotenuse of this triangle. The x secant would be the part that sticks beyond our unit circle. So that would be, looks like secant theta minus 1. 1 would be our radius of the unit circle. So this right here would be the x secant, which would be secant theta minus 1. Then we also see the x cosecant, and that's the same idea with the cosecant goes from the origin out to this point. Well, the x cosecant would be cosecant of theta minus 1. So And let's see, there probably are some other interesting little trig functions that have been defined, but like I said, I've never dealt with even versine or haversine or any of those. There are uses for some of them anyway, but very particular, focused applications where if you go into a very specific job or career, you may run into those, but most of us will never see them again. But those are some of the interesting trig functions that we can kind of expand our knowledge of trig a little bit. So that's pretty much what I wanted to cover today.